Algebra 2, Chapter 15, Section 4, Applications of Series. If air resistance is neglected, a falling object travels 16 feet during the first second after its release, then it falls 48 feet the next, then 80 feet the next, and so on. First, is this sequence arithmetic or geometric? So if it were geometric, we should be able to take a common ratio from the terms and it would be the same. So 48 over 16 is 3, 80 over 48 is 1.6. So it's not geometric. If it's arithmetic, we should be able to subtract them and come up with a common distance. 32, 80 minus 48 is 32. So the answer is arithmetic, and the distance d is 32. What is a sub 4? Okay, so 16 is a sub 1, 2 is 48, 3 is 80. So adding 32 to 80, we get 112. What is a sub 5? The number of feet it falls the next second. 32 plus that, 144. Find a formula for the nth term in the sequence. So we could just find the nth term would be a sub n, which is a sub 1, or 16, plus n minus 1 times the distance, d, 32. Calculate, oh, I'm sorry, that's the sequence, yes. So now calculate S1, S2, and S3. So the sums, so S1 would be 16 feet, the total distance it's fallen. S2 would be 16 plus 48, 64 feet, and S3 would be 64 plus 80, which would be 144 feet, total feet that it's fallen. Give a formula for S sub n, the total distance fallen. Well, we can just use the the series formula for arithmetic series. So going into the book and finding that formula in 15.2, it was 1/2 n times 2 times the initial sequence entry, 16, plus n minus 1 times d, which is 32 for us. So doing some simplification in this particular case, we have 1/2 n 32 plus, and then multiplying this out, 32n minus 32. So 32 plus minus 32 is 0. Multiplying this out, we get 1/2 times 32 is 16. N times n is n squared. So the total distance fallen is 16 n squared. An annuity account earning 3% APR, which means annual percentage rate, is compounded annually. Payments of $1,000, which means withdrawals from the account, are made each year after the interest is deposited. So an annuity is a kind of investment you put money into, and then you get a payment every year. That's why it's called annuity, because you get something out of it every year. First question, what initial balance needs to be deposited so that the account balance remains the same every year? So we'll put in some amount of money, say $50,000, and if we put in the right amount, as we get the $1,000 out every year, the interest we make will make up for the $1,000. So if we think about the balance after, so let's say B2, balance after the first year, is the balance at year 1, or the initial year, okay, times the interest we earned from that balance, 1.03, minus the $1,000 payment that we just made. And what we're wanting is for B2 to be the same as B1. In other words, the balance after I get my interest and take out the 1,000 is the same as what I put in. Okay? So maybe we should write, we want B1 to be the same as B2. So now we have this equation that's just got B1, which we can solve. So B1 equals B1 times 1.03 minus 1,000. So subtracting from both sides, we get this. factoring out B1, we have 1 minus 1.03 equals minus 1,000. So the initial balance, in order for this to happen at 3% interest, would have to be, and $1,000 payments, would have to be minus 1,000 over 1 minus 1.03, or $33,333.33. So $33,333.33 has to be the deposit amount in order to be able to take out 1,000 every year and keep the balance the same. So suppose, for this is part A, suppose for part B we couldn't do that. All we had was $20,000 to put into our annuity. When would we run out of money? When would our annuity have a zero balance? So we'll need to model a geometric series in order to do this. So our common ratio R is our rate, 1.03, and our initial amount we're putting in is 20,000, but the series, the sequence is that we're getting $1,000 payments out of the account. Okay, so we're getting $1,000 out. So every time we take out 1,000, we're also losing out on the interest of that 1,000 that we would have had. So we would have, after, think of this for us, so that we start with what we put in, which is 20,000. Then in the second year, we get our interest on the 20,000, and then we lose our $1,000 that we got out. Okay. The third year, our balance would be what we had in the second year times 1.03 minus the 1,000. Okay. So if we think about how this is going to play out over time, let's plug in B2 just to see this. So B3 will be 20,000, 1.03 minus 1,000 times 1.03 minus the 1,000 we took out. Okay, and if we factor this 1.03 in, we get 20,000 1.03 squared minus 1,000 1.03 minus 1,000. So it looks like geometric growth except for this first term, which is different. Okay, or really it's like not growth, it's a geometric series here. Geometric sequence is going to be with this 1,000, so we'll put this first term all by itself, and then we'll make a geometric sequence out of these thousands and the 1.03s in order to make a series. We'll use the series formula to find our balance. So if we think about this other part over here that's geometric, it's like we started with negative 1,000. We're kind of modeling what we're taking out as our geometric series. Okay. So after the nth year, our balance Bn would be 20,000 1.03 to the n minus 1, because we have the 1.03 comes out. Okay, so then we have, so here we have 2 with the 3, that's why it's n minus 1. Then we have this geometric part, which is like having 1,000 to start with, and then our ratio is 1.03, and so after at Bn, we've only been able to have n minus 1 that we've taken out. Okay, so remember the formula is n. So for this part, since it's n minus 1, it'll be n minus 1. Because the part we're taking out is like delayed a year, basically. And then divide by 1 minus 1.03. So here's a formula for our balance. over time. Now, what we're interested in is when is this equal to 0? Okay? And we're going to have to solve for n. So we would have, running out of space, so we'll just kind of work over here. We'd have 20,000. So if they imagine this equals 0, we can subtract 20,000 1.03 to the n minus 1 onto the left side of the equation. And then we can divide these 1,000 on both sides. So if we have 20,000 1.03 into the minus 1 on the left-hand side, it was negative. But we'll have negative on both sides, so we'll just cancel that negative out. 1,000 1 minus 1.03 to the n minus 1 over 1 minus 1.03. Then we have this. We can divide both sides by 1,000 and cancel out the thousands places of the lower numbers here on the 20,000. Left with 20. 1.03 to the n minus 1 equals 1 minus 1.03 to the n minus 1 over 1 minus 1.03. So we can multiply both sides by 1. I'm sorry, I've got this wrong. I've copied this wrong. The parenthesis is on the outside of the, not the inside. Remember, the n minus 1 applies to the 1.03. So we can go ahead and do this subtraction. 1 minus 1.03 is negative 0.03. Then we can multiply the negative 0.03 by 20. Okay, we would get negative 0.03 times 20 is negative 0.6. Negative 0.6, 1.03 to the n minus 1 equals 1 minus 1.03 to the n minus 1. Now we can subtract or add this negative 1.03 to the n minus 1 to both sides. We'd have minus 0.6 1.03 to the n minus 1 plus 1.03 to the n minus 1 equals 1. Okay, and we could factor out 1.03 to the n minus 1 on the left, and we would be left with 1.03 to the n minus 1, and we'd have negative 0.6 plus 1, which is 0.4. Okay, which tells us that 1.03 to the n minus 1 equals 1 over 0.4, which is 2.5. Okay, now taking the log of both sides, we would get log of 2.5. Sorry, log, let's do it right, log of 2.5 divided by the log of 1.03, and that gives us n minus 1. Okay, so n minus 1 is 31. Okay, and so what we need to remember here is n minus 1 lines up with our b's, but b sub 1 is the balance when we start, which is at the beginning of year 1. Okay, so if we're thinking about the end of how many total years, we really need to think about n minus 1 as our total years, because so n is 32, but because our first n is 1, 32 minus 1 is the number of years, or 31 years. So we would have 31 years before we run out of money. A patient is given a 250 milligram injection of a therapeutic drug. Each day the patient's body metabolizes 20% of the drug present, so that after day 1 there's 80%, or 4/5 of the original, so that after 1 day 80% or 4/5 of the original amount remains. After 2 days 16/25 remains, and so on. The patient is given a 250 milligram drug every day at the same time. What is S sub n, the drug level after the nth injection? Okay, so we have 250 milligrams every day. and each day it metabolizes 20%. So our ratio is 4/5. And our initial amount, A sub 1, is 250. And that gives us our amount of drug each day from one injection. But we're doing an injection every day. So it's like summing up. And each day we're one day behind. So we can sum up the sequence in order to get how much we have in a particular day. So what we could write then is the quantity on day n is equal to the series, or the partial sum on day n, which would be 250, 1 minus 4/5 to the nth power over 1 minus 4/5. Okay, and so how much remains after the 10th injection? Well, we could take n is 10, 4/5 to the 10th power. 1 minus that is 0.892, divided by 1 minus 4/5 is 0.8. 4.46 times 250 gives us 1,115.78 milligrams is present. And just thinking about this idea, over time what's going to happen is the amount of drug is going to kind of stabilize. And that's called converging. So whenever we have a geometric sequence where the common ratio is less than 1, the sum, or the series, has a convergence. The series will have a value that it will converge to if we make the entire infinite sum. So we've been talking about S sub n, where n is some index. Well, if we think about n being infinite, so if we take the sum of our sequence values and we try to push the number of values to infinity, to as many as we could think of, we can have this idea of a limit, which we'll introduce in calculus, which I don't want to tell you anything more than it just means when n gets super big, okay? N gets really, really big. So as n gets really, really, really big, r to the n is going to become 0. So r to the n is going to go to 0 as we get really, really big with n. And that's because, think about it, anything less than 1, 0.7. Every time we raise it to a higher exponent, it gets lower and lower and lower and lower and closer to 0 until we get really, really close. So as we get to infinity, which of course we never really can get to, this value becomes 0. Since this value is essentially 0, we're left with this convergence value. Okay, so you need to memorize this convergence formula. And all you really need to remember is that the r to the n goes away, becomes 0. So we just have our initial value a, which we're calling a sub 1 for our sequence, divided by 1 minus r. That's our convergence value. If r is greater than 1, the series diverges and there is no convergence value. So if we go back here and we think about, we add this ask the question, what is the long term or the convergence level of the drug? Then we could use the formula where this goes to 0. Okay, so we would have 250 times 1 basically over 1 minus 0.8, and 1250 is the long term. 1250 milligrams is the long term amount. So we can now talk about this next example. To wean himself off snacking on M&Ms, a man resolves to eat 7/8 of the number of M&Ms the next day compared to the previous day for the rest of his life. He begins by snacking on a whole package of M&Ms each day. How many packages does he need to satisfy his needs for the rest of his life? So the first day he'll eat a whole package. The next day he'll have 7/8 of a package. The day after that he'll have 7/8 squared, or 0.765 of a package, and so on. Okay, and so how many does he need for the rest of his life? That's convergence. We're asking what's the long-term or the convergence number of packages. So if you remember, he starts with 1. That's so A, the convergence value is A divided by 1 minus R. So A is 1. He starts with 1 package, and he eats a ratio of 7/8 the next day. So we have 1 over 1 minus 7 over 8, or 8 packages that he would need to finish off all the M&Ms he would eat for the rest of his life. 8 packages. Now this example is a little far-fetched because he would have to be eating like half and a quarter of an M&M at some point. Clearly, you would just probably finish that last package, the last M&M of your life, and go on. And this last example used a geometric series to write the repeating decimal 0.04, 123, 123, 123, and so on as a fraction. So to do this, we're going to leverage the convergence value. Okay, since this is an infinite sequence that always repeats, the convergence value is we're going to use that idea to do this. So if we think of this decimal, we can break it up into some parts. 4 hundredths. This is first part. And then the parts that repeat are 123 over 10,000 plus 123 over 10 million plus 123 over 10 billion. So this first part is all by itself, but this part is a geometric sequence. And this geometric sequence is A of 123 and R, the ratio is 1,000. We're increasing by 1,000 each time. We're dividing by, ratio is not 1,000, it's 1 over 1,000. We're going thousandths each time, right? We're shifting 1,000th over on our decimal. So we're multiplying by 1 over 1,000, or dividing by 1,000. So now we can use our formula, A over 1 minus R is our convergence value, to find what this sequence will converge to in a ratio, okay, which is a fraction. So this is the way we do this sort of trick to write repeating decimals as a fraction. So A would be 123, and R is 1 over 1,000. So 1 minus 1 over 1,000, if we think about that for a second, you would have 1,000 over 1,000 to minus 1 would be 999 over 1,000. So denominator, you'd have 123 over 999 over 1,000. Okay, so using the complex fraction stuff, it'd be 123 times 1,000 over 999. Sorry, no, that's wrong. Let's erase. It's 123 over 1 is the numerator in the complex thing, and then we have to reciprocate the 999 over 1,000. So we would have 1,000 over 999. This still isn't right. So what have we done wrong here? 123 999. So if we think about, let's see what we've done wrong. So we've got 1 minus 1 over 1,000 and 123 over that. So that gives us the wrong answer. So something I've done wrong at the very beginning. 123. Yes, our initial value is 0.123. or 0.00123, because it's this whole part of this decimal. So it's really 0.00123 over 0.999. See how that works? 0.00123. Okay, so it's and we could think of that as this is really 123 times 1 over 10,000. Okay, I left that 1 over 10,000 factor out of my a, which I needed. Okay, it's really it's of course a is this 123 over 10,000, not just 123. Okay, so that fixes that. Okay, so we really have 123 over 10,000 in the numerator. $123 over 10,000 times 1,000 over 999. Okay, so that leaves us with 123 over 9. We're still off by a power of 10 somewhere. So this should be 100,000 somewhere. What have we done wrong? Yeah, 0.00123. So 123, let's just verify. 123 over 10,000 is 0.0123. So that's what I've done wrong from the very beginning, because I got this tens digit wrong. Should be 100,000. Sorry about the mistakes. That shows you that anyone can make a mistake with these things. So it's really 128 over 100,000. So we have 123 over 100,000, sorry. So you have 123 over 100,000, and the 3 zeros cancel. You're left with 123 over 10 times 9, 100 times 999, 99,900 in the denominator. Okay, so let's check it. 123 over 99900 should give us everything with a 0.04. So we have the 1, 2, 3's repeating. Okay, now we need to add our 400ths to this fraction to get the total fraction. So we would have, in order to add, we need a common denominator. We need to multiply this by 999. So both the numerator and denominator times 999. So we have 4 times 999, 3,996. 3,996 over 99,900 plus 123 over 99,900. Adding them together, we get 4,119. 4,119 over 99,900 is the answer. So we should be able to take a calculator, 99,900, and we should get the what we asked about, this decimal point, 0.04, 123, 123, 123, and so on. And that is the answer.